So how do we work with a system like this? Well, the honest answer is I don't know. Programming that original transfer system that looks like a microcoded machine, that's straightforward. It's complex and confusing, but the steps can be described very programmatically. Programming this chemical-based system, the EXIST system, I don't know how to do that. The challenge is to see what the system is capable of, and one idea is instead of trying to force it into doing something, let it do whatever it does and try to detect what we consider to be interesting behavior. And there's a number of ways we can describe what it means to be interesting, and how we choose to look for that is going to affect what we discover. But nonetheless, a first step to working with this is being able to simulate it. And simulation is pretty straightforward. If we go back to our spatial domain and imagine that it extends over 40, discretize space not into infinitesimal tubes, but small tubes. And so for the sake of argument, we're using 8 tubes per integer. So this is 0.125. And there's some sort of height to these tubes that describes how much volume of chemicals you can have. And we have some sort of mix of source and destination sitting in these tubes. And the question is, how can we see how the system changes across time as we let these tubes execute their commands, do their source-destination transfers? So we have a structure in memory that stores the amount of source and destination in each tube, or we've broken the space up into 320 tubes in this case. And we simply begin with the first tube. We look at the amount of source, the amount of destination, and based on the concentration of chemicals in those tubes, we decide how much chemical is going to flow from that source tube to the destination tube. And we record that delta, but we don't change the concentrations yet. And then we go to the next tube and we say, what does that say we should transfer? And we add that delta to whatever deltas we've computed so far. And we move all the way across here, and we're basically integrating across space and finding the total contribution of transfer from any tube to any other tube. Now, in addition, as we're doing that, we're doing 2 other things. One, we're assuming the transfer runs for some period of time, delta t, which for argument's sake could be a 20th of a second. The units are arbitrary, but 0.05. And so whatever that transfer says is based on some sort of base transfer rate, and in this case it's scaled by how long we're letting time increment. And the assumption is that during this period of time, no concentration is changing. The instruction that this is directing is constant across this period of time. Even though in reality, while this transfer is taking place during this period of time, something else is pulling chemicals into or out of this tube, which is changing this instruction. But we ignore that. We discretize over 0.05, so it's like doing a finite element approximation. The other thing we do is that when this says transfer, from example, from tube 4 to tube 7, we don't just tally a delta from tube 4 to tube 7. We go back to this e to the minus x squared shaped curve, and we say, okay, 4 to 7 we're going to get a full transfer rate, but from 4.1 to 7.1 we're going to get a little bit less transfer. And from 3.9 to 6.9 we'll similarly get a little less transfer. And from 4.2 to 7.2 we'll still have a transfer, but it'll be even lower. And down here from tube 5 to 8 we might get half the transfer rate. And the thickness of this curve, the degree to which it flares out, that's configurable in the simulator. That's what we call the effect. And we can set that to whatever value we want. So we do this across the entire space for this small time interval. We figure out what the deltas are, and then we sum them up. We do the integration, and we find what the new value of the chemicals are in each tubes. And now we advance our time by this amount, and we begin again. And we just keep doing this, and the goal is to see how chemical transfer changes across time. And the software tools that are available on GitLab are doing this in various forms. Some of them are very straightforward transfers, some of them are built around the idea of seeing an initial setting of chemicals as a genome and trying to evolve a population of systems that do some interesting task, mimic some behavior or respond to certain stimuli, and so on and so forth. And there's a number of variety of these, and we'll talk about these varieties in subsequent videos, as well as looking at some videos how we actually use some of the simulation tools to see what happens as we run this. But this is the basic idea of how the simulation behaves.